What is up, ladies and gentlemen? So, as agreed, Christmas isn't over yet, but here we are with another stream. So, as previously discussed, today, or rather in this video, we will be wrapping up the first part of our AMF syllabus by talking about Binomial Theorem, and thereafterwards we will leave behind algebra and powers and exponents and all that stuff, and we will instead move on to coordinate geometry thereafterwards. So I think this video probably will not be super long. Definitely it will be shorter than the one we had for logarithms, etc. Right? So let us begin. Alright, so for today, we will be looking at binomial theorem. And for this topic, I'm going to be honest, it is not an extremely important topic in your AMF syllabus. So I would like to minimize the amount of suffering we have to go through. Now, before we begin, there are a few preliminaries we need to be aware of. First of all, before anything even begins, we need to first recognize what factorials are. So, as far as you need to know for your level, factorials are essentially a situation where you multiply by all the numbers one step lower than you, starting from yourself. For example, 6 factorial, which is written as 6 exclamation mark, we will simply start from 6, and then we will go one step down to 5, 4, 3, 2, 1, and then we will stop there. Now, obviously, we will have to stop right before 0, because imagine what happens if you didn't stop and you went all the way to 0. Very quickly you will realize that you would have played yourself, right? You're just going to get 0 again, and therefore the entire factorial concept will be worthless. So obviously we're not going to do that. Let's not play ourselves. We will stop at 1. Do also take note that because we are stopping at 1, your calculator will tell you that 0 factorial is 1. This is hard-coded by definition. Right? And you might be thinking to yourself, wait, it doesn't make sense. I start from 0 and then go down, I go down, I go down. But you must remember what we said, you can't even include 0. So actually 0 factorial is a bit of a dirty concept, right? And for convenience sake, you can just take for granted at this level that it will be equal to 1. Another preliminary idea we need to be aware of is the concept of combinatorics. If I have two different numbers, preferably whole numbers, right? We are dealing mostly with whole numbers in this topic. I can actually write something known as n choose r, which will be written NCR or n bracket r, right? So it could be written like this, it can be written like that, it can be written like that, it can be written like that. There are many different ways of writing n choose r, and it represents the number of ways you can choose r objects from n objects. This choosing only cares about the objects that you have collected. We don't care about the order of collection, right? And n choose r happens to have a formula behind it, which we don't need to worry too much about. This formula will be given in the actual examinations. N choose r is always equal to n factorial over r factorial multiplied by the factorial of the difference, n minus r, right? Very convenient formula, and you can actually go on to simplify it as such. This formula over here, this second one, looks a little scarier. Most people are not fond of it, so it might be easier to demonstrate with an example. let us try, for example, if I were to tell you n choose 3. By formula, this will give us n factorial, 3 factorial, n minus 3 factorial. Now, n factorial over here will simply be n, and then afterwards we'll multiply by one step back, one step back, one step back, one step back, blah, 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 all the way until 1. Agree? Whereas for the denominator, this will be more interesting. 3 factorial is obviously just 3 times 2 times 1. How about n minus 3 factorial? So n minus 3 factorial here will actually give you n minus 3. Afterwards, one step back, one step back, one step back, until 2, until 1. So what we will realize is that this portion here actually repeats itself, allowing us to cancel away all these extra terms, from which we will go on to get n minus 1, n minus 2 over 3 times 2 times 1. And indeed, over here, n choose r, right? If we compare this and that, the main point will be that r equals to 3. And we see that the denominator here will be 3 factorial as desired. And the numerator, right? The numerator starts from n, right? From n at the bottom. And it counts down all the way until n minus r plus 1. But in this case, we have r equals to 3. So it counts down until n minus 2, which we see over here. And therefore, this formula is, or rather this simplification over here is what we have over there. Right, so just as a simple example, there are a few funny things, a few special cases that we can pay special attention to. The 4 special cases have been given in the bottom of this page, but honestly it is not particularly difficult. For example, if I have n objects and I want to choose 0 objects, obviously there's only one way to do it, and that one way is to do nothing, choose 0 objects. If I have n objects and I want to choose only one object, naturally that will give me n choices as well. For example, if I have 5 fingers in one hand and I want to choose to lick only one finger, you have 5 fingers to lick, right? 5 fingers to choose from. I can either lick the thumb or the index or the middle finger or the ring finger or the pinky. The point is that you're only licking one finger, so it's quite simple. You just choose the finger you want out of the 5, bam, we're done. Right, so this is somewhat straightforward up to this point. Let us move on. What we're going to do next is we will take a look at the situation 1 plus x to the power of n. And then n itself is going to be an integer greater than or equal to 0. Right? So if we look at these patterns over here, created by 1 plus x to the power of n, you will notice that the numbers on the coefficients 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, etc., you will realize that these numbers actually can create this funny little pattern over here, where diagonally the entries add up to each other. This funny pattern here is known as Pascal's triangle, and something marvelous and coincidental about binomial numbers, or rather numbers from the coefficients of 1 plus x to the power of n, is that they always seem to match the Pascal's triangle. It's just some kind of freak coincidence of nature. And because of that, it allows us to work out the coefficients of 1 plus x to the power of a large number. Now, even better is that these same numbers 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, etc. These numbers can also be obtained from n choose r. It has a pattern by itself, which I will leave you to observe. And by combining this pattern, we can conclude this particular formula. 1 plus x to the power of n always follows this nice formula, right? The coefficients will be 1, n choose 2, n choose 3, n choose 4, blah blah blah, n choose blah blah blah, all the way until the end. And of course the n will simply be n choose n, which is 1, right? So this pattern over here, this formula, allows us to open up some extremely nasty algebra objects that we previously weren't able to do. Previously in secondary 2, we have learned up to the square, right? I know how to open this. It will simply be a square plus 2ab plus b square. But now, with this number pattern in our pocket, we can open up extremely freaky things that we would otherwise not be able to do, right? So one last thing to take note of is that even though the formula is written like that, it's completely fine for you to understand the formula as having the coefficients n choose 0, n choose 1, n choose 2, n choose 3, 4, 5, 6, 7, blah 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 blah, blah 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 blah, until n choose n minus 3, n choose n minus 2, n choose n minus 1, n choose n. This is completely fine as well. If you are struggling to see this in action, then you might want to revise some of the special cases of n choose r from the previous page. Now, more generically, if you have any random objects like a plus b entire thing to the power of n, then this will be the formula. Once again, observe that the coefficients will be n choose 0, n choose 1, n choose 2, blah blah blah. And of course, n choose r, the formula, as we saw just now, will be given in the exam. Now, in the exam, the simplified formula of 1 plus x to the power of n, which is this one over here, at the bottom, this formula will not be given to you. But in the exam, you will at least get the uglier looking one, which is this, the more helpful looking one. Now, there is also a pattern in the first object A and the second object B, which is that A will start from n and decrease by 1 and go towards 0. Whereas B will start from 0 and increase by 1 and go towards n. And of course, because of that, the total of the power is always going to add up to be n, which makes sense because the original algebra on the bracket has a power of n as well. Right, so let's not waste too much time staring at the formula. It might be better for us to get our hands dirty with some exercises. Right, so let's take a look at the first exercise. For example, we have 1 plus 2x, 5. In this case, clearly a is 1, b is 2x. And because a is 1, we can actually use this simplified formula, right? So memorize this formula. I will be scrolling away. And therefore, we will simply say that I have 1 plus 2x to the power of 5. This 2x person will be replacing the position of x in this previous formula, right? And therefore, I should expect to see 1 plus n x, take note of the round brackets, please, plus n choose 2. Remember that n is 5, yeah? The power of the original binomial. We call it binomial because there's 2 objects inside the bracket, hence bi. So n choose 2, x squared, plus n choose 3, x cubed, plus n choose 4, x4 plus n choose 5 x5. So you notice that the x, in this case the second object, will be the entire second object. That's why we put it inside round brackets. Of course, from here, if you are familiar with Pascal's triangle, you should remember the special numbers will actually be 1, 5, 10, 10, 5, 1, and therefore we have the following result instead. 1, 5, 10, 10, 5, 1. Like this. From here, it should be a simple enough affair to open everything up. Like so, right? And therefore we have suddenly evolved, right? In secondary school we only learned 1 plus x squared. Now we can do power 5. We can even do more than 5. Let's take a look at the third exercise here as well. 5 minus x, 6. So in this case, a equals to 5, b equals to negative x. Why is it negative x? If you look at the formula over here, it is always written as a plus b. So we are forced to say that this guy over here is actually 5 plus negative x. And from here, we have squared. And then you work on. So without further ado, let us try it out. The formula here will be dramatically uglier, but hey, that's just how it is. So let's zoom out a little bit so that you can keep the formula itself visible. Right, I hope you can put the video in full screen or something. So in this case, we have equals to, and then let us begin. The first thing will be a to the power of n, so a to the power of n. Like so. Afterwards, we will plus n choose 1. And then afterwards, a to the power of n minus 1. In other words, 5 to the power of 6 minus 1, 5. And then we have b by itself. And b is the second object, negative x. Then we will plus n choose 2. And afterwards a, which is 5. N minus 2, in that case that will be 4. And afterwards b2. b is negative x, so we will have negative x2. And we will continue on the pattern. So n choose 3, a to the power of n minus 3, in this case that will be 6 minus 3, which is 3. And afterwards b to the power of 3. Plus n choose 4, and in this case we will have the following. And then so on and so forth. We will continue working this out. And of course, the last one, 6 choose 6, n choose n, will simply be 1. So let's just omit that and have b to the power of 6, b to the power of n, right? As stated over here. Once you have this, then you can slap everything into the calculator and start working it out. Of course, please make sure you know where the button is, right? The n choose r button on your calculator. For most scientific calculators, it should be written as NCR, like what we saw earlier. Right, so you will be able to let your calculator handle everything here, and this should give you some nice results. The numbers will be pretty big, but at least we will not be seeing any fractions in this particular problem, so I consider that a win. One other thing is, of course, do be mindful of the minus signs, right? You notice that some terms have a double negative and some terms don't. As a result, we will actually see that the plus minus will be alternating. I start with a positive, then I go to a negative, and from there it becomes plus minus, plus minus, plus minus, so on and so forth. right? From here, it just becomes plugging your calculator. Please don't do this mentally. I know some of the earlier topics I was doing everything mentally, but for binomial theorem, due to the size of the numbers you're working with, you probably don't want to do that. For anything with combinatorics and probability in general, you just don't want to do things manually. That is a very painful idea. Right, so once you open everything up, then we will be done with all these expansion type questions. Okay, so the next thing we need to talk about is something known as the the general term. So the general term simply says that if you look back at the formula of binomial theorem, there is always one part of the formula that is like this: n choose r, a, n minus r, b, r. Now if you look at this as the first object, and you look at that as the second object, and you look at this as the third object, you will realize after doing a bit of counting that this over here will be the r plus 1th object, right? So if I minus 2, it will be the third object. If I minus 3, it will be the fourth object. If I minus r, it will be the r plus 1th object. Why is this helpful? This is helpful because I can zoom into a specific object created from the binomial rather than having to open up the entire binomial just to find a single person. For example, if I only want to find x squared, then I don't need to open up everything. I can just zoom into x squared. So this method of zooming in will use the general term. We will write the general term like this. We'll write it as t r plus 1, where in this case t stands for term, right? So the r plus 1th term. So aside from letting us zoom into a specific object, it also allows us to check for the existence of an object in the first place. For example, if the question wants you to deliberately find the constant, then you can use the general term to zoom in and look for it. If the question deliberately wants you to find x to the power of 4, you can use the general term to zoom in and look for it. So 2 exercises are given over here. The first question has already been filled in for us, so I will leave you to take a look at this by yourself. The second problem is a little more interesting. They want you to find the constant term of that really ugly person over there, where the inside has x squared and 1 over x, and the outside has a gigantic power of 12. Right, so let's take a look at the second problem together. They want us to work with this particular person over here. So what we will do is, just like the first problem you see above, in order for us to use the general term, we should need to explain the context first. So we will say inside 1 over 15. Oh, you don't even need the 1 over 15. Let's ignore the 1 over 15 for now, since it is just a multiplication stacked at the very end, right? So let's focus only on the binomial portion. Inside x squared plus 1 over x, entire thing to the power of 12, the general term is t r plus 1 equals to, and then we will use the general term formula from the formula sheet above. N choose r, a, the first object, n minus r, b, the second object, r. So this is what we will declare. From here, we will see that there are a few simplifications that can be done. In particular, notice I can use the laws of indices to change the middle person into 24 minus 2r and the person at the very back side into negative r, negative indices. And from here, we can combine all of the x objects together like this. Do take note that it will actually be addition, it's just that we are adding with a negative object. So it still gives us 24 minus 3r. Alright, now that we are at this stage, then we can go on to ask ourselves, what is the question looking for? We're looking for a constant. So I'm going to tell them, for a constant, what does it mean? A constant means we have the number only, the coefficient only. There is no algebra. So you can imagine it as x to the power of 0, because we know that is equal to 1, which is a constant. So the power, which is 24 minus 3r, must be 0, implying that r equals to 8. Right? And therefore, the constant term of the original math problem, which is 1 over 15, and then the binomial. Therefore, the original math problem has a constant term of 1 over 15 multiplied by t r plus 1. R is equal to 8, right? So I'll have 8 plus 1. From here, then we can plug in the numbers. 1 over 15, 12 choose 8. X to the power of 24 minus 3 times 8. And this will give us 1 over 15 multiplied by 12 choose 8. And then we can just ignore the x, because we know 24 minus 3 times 8 will be 0. It will be x power 0. It will be 1. Right? That is the whole intention. So we'll feed this in, and once you press 1 over 15 times 12 choose 8 into the calculator, you will get 33, which is what we wanted to show, QED. Alright? So that covers basically everything we need to know about binomial theorem already. Now all we're left with is applications. For example, can we use binomial theorem in the multiplication of polynomials? Can we use it in estimation? Can we use it in surds? Can we use it to work backwards and find the value of the power instead of the person inside the bracket? So that will be our focus for the remainder of the content here. Now, some questions will ask you to play around with multiplication a little bit. So just as an example, a practice, I will go through the second problem on this page. Let's take a look at problem number 2. They want us to fully expand 2k plus x to the power of 4, entire thing to the power of 4. It says fully expand, so you're going to have to write down every single object. Of course, by Pascal's triangle, you might remember by now that the numbers will be 1, 4, 6, 4, 1. Right? The coefficients will be 1, 4, 6, 4, 1. You can Pascal's triangle it. If you want to press everything manually, then you can. Right? So in this case, we'll have 4 choose 0, 4 choose 1, 4 choose 2, blah, 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 blah. It will be a very messy affair, so I shall not go into such tedium of detail. From here, then we can go on to open up all of these round brackets. We should get 16k4 plus 32k3 x4 plus 24 k square x8 plus 8k x12 plus x16, and we are done. Right? From here, the next part will then ask us, the coefficient of the x to the power of 8 person is 29. By finding the general term, can you show that k equal to 1? It's a proving question. Of course, they kind of already gave you a hint, right? They told you, okay, yo, just find the general term first, man. Don't think so much. So you know what? Let's take their advice. Inside this second binomial, 1 minus x squared to the power of 5, the general term will be tr plus 1 equals to, and then we'll use the formula from before and choose r, a, n minus r, b, r. Very clearly, this will simplify into this result. Right? So, looking at this, when we look back to the math question, what does the math question say? It says that x to the power of 8 inside this guy is 29. And if you look at this guy, right, the first one is what we are doing right now. The second one is from part 1. So we might as well handle the first one, the one with 1 minus x squared to the power of 5. The question says x to the power of 8, so we will say for x to the power of 8, what do we need? We need the power, which will be this portion over here. This guy will be equal to 8. So for x to the power of 8, it is clear that we have r. Oh, that is the wrong shade of green. We will have r equals to 4. And from here, we have t4 plus 1 equals to 5 choose 4, negative x squared to the power of 4. And this gives us a total of 5x to the power of 8. Now, the coefficient of x to the power of 8 inside the sum of these binomials is 29. And that means that the x to the power of 4 object from the part 1 person, right, from the green zigzag person, from this guy, the x to the power of 8 person, which is here, right, he must add up. He must add up with our 5x8 over here in order to get the person that we have described in the question, which is 29. And from here, very clearly 24 k squared will be equal to 24. In other words, k squared equals to 1. Once you have k squared equals to 1, then we are almost done. Do make sure to pay attention to the original question. It says k is a positive constant. Therefore, what we will do is k equals to plus minus square root of 1. Since k is positive, k will be equal to positive 1 and not negative 1. And QED, that is what we wanted to find. Of course, if the question doesn't say whether k is positive or negative, then you're just going to have to take both. Nothing wrong with that. Right? So from here, let us move on to the next situation. Now, sometimes in order to, this isn't really useful in real life anymore, but sometimes in order to test your creativity, we will deliberately ask you to use binomial theorem in order to estimate some really funny decimal powers, when in reality, of course, in real life, you will just press it into the calculator. Of course, centuries ago, calculators were not a thing, so it made sense back then. Nowadays, we just test this in order to make sure that you know how to work with your algebra. So let us work with, for example, let's work with problems 2 and 3 over here. Right, so problem 2 tells us we want to expand that thing over there up to and including x cubed. So this is a little more interesting. Notice the terminology, right? Up to and including x cubed. In other words, the math problem only wants to see up to x cubed, and anything afterwards, like x power 4, x power 5, we don't care. You can skip it. So let's do exactly that. We have 2 plus 2x to the power of 8. You can use the formula immediately, or you can be smart and factorize out 2, like so. However, do keep in mind that based on your laws of indices, the factorized 2 will have the same power attached onto him as well. Once you have this, the remaining portion should be quite straightforward. We will use binomial theorem on the second person, on the first person 2 to the power of 8, you're just going to feed him into the calculator. So let us do exactly that. So over here, we will use the simplified formula for binomial theorem, which was from 1 plus x to the power of n, right? We will use this simplified formula. So in this case, I have skipped a few steps over here. I'm sure you can figure it out by yourself. And then from here, of course, the last thing we need to do is to add or rather multiply the 256 back in. Notice that in order to represent the fact that there are other objects and we simply ignored those objects, we're going to write plus ... at the very back side, right? We're just going to abuse ellipses to represent the other objects that we have considered to be irrelevant. And this whole thing will be our answer. From here, they want us to estimate the value of 2.02 to the power of 8. So if the inside 2 plus 2x was to be equal to 2.02, then of course x will be equal to 0.01. I'm sure you can figure this out. And therefore, we can estimate 2.02 to the power of 8. We will say that this is equal to 2 plus 2x to the power of 8 when x is equal to 0.01. And from here, we will estimate it to be equal to our answer in part 1. Our answer in part 1 without the ellipses. That's why I use the estimation symbol, because this time round, we decided that, okay, everything after x power 3 is irrelevant. So I'm not even going to write it in this time. I'm just going to cancel it. And I'm going to say, okay, this isn't the perfect answer. This is an estimate. From here, of course, you will be using your calculator all the way. So 256 plus 2048 times 0.01 plus 7168 times 0.01 square plus 14336 times 0.01 cube. Feed this whole thing into our calculator and you should get 277.211136. And the question wants 2 decimal places, so we will have 277.21 to 2 decimal places, and we are done. Honestly, not very enlightening, but on the bright side, it's also not very difficult. So the next problem asks us, show that we can estimate 3x squared minus 2 entire thing power 7 into x squared, x4, and then a constant. So in this case, the fact that the constant is over there means that we must be counting from smaller powers and then to bigger powers. So in order to make sure that we are indeed counting from smaller powers, right, what we are going to do is, before we invoke binomial theorem straight away, we are going to deliberately swap the order of the objects to put the number in front. Because if you remember your binomial theorem, it starts with the first object to the power of n, and then it counts the second object from there. So if you want your algebra to start from a constant and then move upwards, the algebra person must be the second object, no matter what. From here, we will go on to use our binomial theorem formula. Like so. And of course, this will then give us negative 1 through 8 plus 1344 x squared minus 6046 x4 plus dot dot dot, which will then be estimated to the thingy that they said in the original math problem. So over here, extremely straightforward, honestly. However, they go on to ask you, given that x itself is a positive number, explain what affects the usefulness of the estimation. Usefulness, in other words, the accuracy. How reliable is it to estimate the entire thing power 7 into something that's just number, x squared, x4? To answer this question, we will need to ask ourselves, what did we throw away? Think back to how we did estimation with numbers. The person we throw away, right? The person we toss aside will always be someone who is irrelevant. So for example, 3.21 estimate to 3.2, we will toss aside 0.01. We will say he is irrelevant. Why? Because he is small. He's not big enough compared to the overall final answer. So ask yourself, who did we throw away here? We have x power 0, we have x power 2, we have x power 4. That means we must have thrown away x power 6, 8, 10, 12, 14. We threw away all these x's that had big powers. So in what situation will you have a big power create a small result, create an irrelevant result? The answer is straightforward. We will have an irrelevant result from big powers when x is small. To be accurate, x must be small. In other words, x will be between 0 and 1. It is very easy for us to demonstrate this actually. Let's say we have, for example, x equals to 1 over 10, i.e. 0.1. The moment you have big powers, such as 6, this turns into something very tiny. And if you have all the way until 14, like in this question, then it will be even worse. Right? So we will have this scenario over here. So it just gets smaller and smaller and smaller. And after a while, when you're dealing with numbers like 10, 100, 200, something as tiny as 0.000000000000001 doesn't matter anymore. So we will say that in order for the estimation to be accurate and therefore useful, x will be between 0 and 1. Of course, my open question for those of you watching who are in my class will then be, what if we threw away the small powers, like the constant, and x power 2, and we kept the big ones like x power 14, x power 12? In that case, what can we say about x? I will leave you to think about this for yourself. Now, the next scenario we need to be aware of is problems where they want us to use binomial theorem to work with trinomials. Binomials have 2 objects inside them. Trinomials obviously have 3 objects inside them. Super ugly. So in order for us to do it right, I'm going to be honest, there's actually nothing smart to do. So let's take a look at question 1 over here as an example. They tell us to open up 1 plus u to the power of 4. Obviously, by Pascal's triangle, we will have 1, 4, 6, 4, 1. From here, they ask us, hence, expand 1, 2, 3 to the power of 4 up to and including only x cubed. So, in order for us to do this, right, and turn the 3 objects into 2 objects, we will just group the last 2 objects together and use substitution. This will change the appearance of the trinomial into a binomial. And you might be thinking to yourself, wait, that's not any better. Only the appearance changed. I still have to open up everything in the future. Yes, yes you do. But at least with the changed appearance, you can go on to use the binomial formula. So once we use u equal to 2x plus 3x squared, it changes back into the exact same thing as part 1. So I will just copy down my answer from part 1. I will deliberately ignore u to the power of 4 because the question says up to and including x to the power of 3. If even x itself only needs to go until 3, then obviously u itself doesn't need to go more than 3 either. From here, then we will have 1 plus 4, and then we will replace all the u's with the actual real life meaning, which is 2x plus 3x squared. From here, you will notice that we have binomial here, binomial there. So you're going to have to do binomial theorem 2 more times within this question. It is a little bit exasperating, but you will get used to it. Now, you will start to notice as you do the second and third binomial theorem that there are some irrelevant objects. For example, this guy creates this person over here, 9x to the power of 4. And to the power of 4 is kind of irrelevant because the question only wants x to the power of 3. So you can actually skive a little bit and be lazy and just focus on the important part, like so. The last one is even better because if you look closely, the first object is already going to be x cubed. Everything else will be even bigger, right? x4, x5, x6. So you can simply focus on 2x, the entire thing to the power of 3, and then plus dot dot dot, like so. Right, so this is what we will have. Let's see, small question in the chat. For quadnomials, we will use substitution as well. You can, that's true. Of course, in pure mathematics, we have a generalized formula. In other words, a formula for the formula, right? For multinomial theorem in general. But that one is way beyond what we need to know. In fact, even in university, you will probably not learn it. It is not helpful. Yeah. So, to answer your question, yes, we will probably be using substitution 99% of the time. Of course, there are a few situations where, you know, you probably don't need it. For example, if I have a quadrinomial that can actually be factorized, then we can just factorize it into 2 different objects and then do trinomial on each of the 2 objects. So that is one example that could possibly work. Anyway, I will talk more about that later. For now, let us return to this problem over here. The last thing we need to do is to tie up all the loose ends. So the front part will be the same. The back part over here, we will have 6 times 4, 24, x squared, 6 times 12, 72, x cubed. And over here, we will have 4 times 2x entire thing cubed. In other words, 4 times 8x cubed. In other words, 32x cubed. And everything else becomes irrelevant. From here, then it is simple enough to combine everything. And we are done. We managed to destroy the trinomial and cut him down into number x, x squared, x cubed. Now, regardless of whether it's binomial, trinomial, blah blah blah, sometimes you might get lucky and you might have a situation where you could actually just factorize immediately. So let me zoom out. I actually have an example of this, which is exercise number 3. Exercise number 3 is quite funny. It tells us to find the first 4 terms in ascending powers. In other words, constant, x, x squared, x cubed. Problem is, this object, in the math problem, the insides can actually be factorized. So this whole thing turns into a joke question because I can just use the factorization and then the whole factorization receives the power 4. Right? So actually this trinomial is a joke. It simply turns back into a binomial. 1 plus 2x to the power of 8. And from here, it will be simple enough for us to get 1 plus 2x power 8. Wait, hold up. There we go. So it will be simple enough for us to use the simplified version of the binomial theorem formula, where the first object is 1. Like so. Right? So this applies even if, you know, by some horrible curse of fate, you end up with a situation where maybe, you know, you have, for example, a quadrinomial, and then you notice that, hey, it's like something that you can actually factorize. So let me give you an example of a quadrinomial right now, actually. Let's say we have this scenario. Looks terrible, looks like the end of the world. So in this case, we have 4 different objects inside the bracket. Worse still, these objects are actually negative powers. We have a constant, we have x power minus 1, x power minus 2, x power minus 3. However, because life likes to play a funny joke on you every now and then, you will realize that we can actually factorize out the inside as such. The inside here is actually just 1 minus 1 over x to the power of 3, like so. Of course, in order to show this, you're going to have to do binomial theorem. So actually what we're doing here is to reverse calculate binomial theorem. I see the 1 minus 3 over x plus 3 over x squared minus 1 over x cubed, and I reverse calculate into this binomial over here, this factorized answer. From here, then we will get back, of course, the power 4, and this gives us the very nice 1 minus 1 over x to the power of 12. From here, it becomes easy to open it up. Like so. So we have combined, working backwards, right? Like reverse calculating of the binomial theorem. We have combined this with the concept of like working with quadrinomial expansion, and we will get this result. It devolves into a binomial in the very end. Right? So it's possible as well to answer the questions in the chat. Of course, typically, once you are dealing with such gigantic algebra objects in real life, then we will have to resort to estimation of some kind, because in real life, when you're doing calculations and all that, if getting 100% accuracy isn't an issue, then you will have problems regarding the speed of your algorithm, right? And of course, how much space it takes up. Your space complexity also becomes an issue. So once we are at that point, that is no longer just calculation, that becomes a problem of like algorithm design already, which I will not talk about. So one other thing we can do is we can actually revisit surds, and we can look for the powers of surds. So for example, over here, problem 1 wants us to expand 1 plus 2 root 3 to the power of 5. In this case, right, they want us to use the full expansion of 1 plus x to the power of 5. So what we will do is we will start with the algebra 1 plus x to the power of 5. Using Pascal's triangle, I will have 1, 5, 10, 10, 5, 1. And so, if I have 1 plus 2 root 3 to the power of 5, it will simply give me 1 plus 5 x plus 10 x squared plus 10 x cubed plus 5 x 4 plus x 5, like so. From here, then you can start to open everything up. Be careful whenever there is an even power, because the even powers will cancel out the square roots. Right? Something like that. Of course, I didn't do every single step piece by piece. That would be a lot of writing that I cannot be bothered to work with. Once you are here, simply combine all of the real numbers together. No, sorry, combine all of the rational numbers together, and then combine all of the surds together. And we are done. Right, so question 2 will be similar. For question 2, right, one trick you can use is to simply factorize out the 2. And then work from there. I feel like that will be easier. Now we're almost done actually. The last kind of problem that we can sometimes see is a situation where the question wants us to find the value of an unknown, but instead of the unknown being inside the bracket, which will allow you to treat it like a polynomial and do, for example, comparing coefficients, what if the unknown is on the power itself? Then you're going to have to use the formula we started with. Factorial and n choose r. And you're going to combine it with all that you have learned so far in order to create a new math problem that allows you to find n. One example problem is given for you on this screen, and while I go for a water break, you can feel free to take a look. Once we have taken a look at this problem, I will go through some practice problems below, and we will take a look at further examples of how to calculate the unknown power in a binomial question. Alright, so water break time. Ladies and gentlemen, we are back, and now I am hydrated. Before I begin moving on to the practice questions, just to point out an observation, for some reason, the Surds video, the square root video, seems to be doing weirdly well. I think people just see like Ramilia in the thumbnail doing like the curl up animation, and then they click on it. So, okay, dude, great. Anyway, since I've been showing the thumbnails for the past few videos, you can have a look at this one as well. Yeah, I'm sure you can understand the joke now that we are at this stage. Alright, so let us move on to the practice problems. Yo, you are massive. Let me zoom up. That's better. Alright, it's true, Ramila's Scala is clickbait, hell yeah. Then again, I think like all of the thumbnails are clickbait because they're like 2-minute Photoshop disasters. Graphic design is my passion, bro. Alright, so let's take a look at the first problem over here. They tell us the natural number n exists such that n choose 4 equals to 6 times n choose 2. Show that n equals to 11. So this is actually a surprisingly straightforward request, right? Just find the value of n, right? Like, how are you gonna mess this up? So n choose 4 equals to 6, n choose 2. We are going to open up the combinatorics on both sides. Once you do this, it is clear that we can cancel the n factorial, and this will give us the following. Now 2 factorial is just 2, so I'm just going to leave it as 2. Over here, I'm going to do a bit of a dirty trick. We have this particular n minus 2 factorial, so I'm going to write it as n minus 2. And afterwards, let's go back to the definition of factorial. You're going to go multiply by 1 step back, multiply by 1 step back, and then continue on and on and on, which I will just represent with a factorial. Once we have this, I think you can tell what I'm going to do. I will cancel this entire thing. Let's also cancel the 6 and the 2. Might as well. From here, all I need to do is to cross multiply and open up all the brackets and then move everything to the left hand side, and it should give us the following result. Once you are here, of course, then you basically already win. All we need to do now is to do quadratic factorization, and we are done. Of course, in this case, the question said that n is a natural number, so we will only accept 11 and we will reject negative 6. And that is exactly what they wanted us to find, QED. So part A, nothing spectacular. Part B is a little more exciting. They tell us to find natural numbers p, q, and r, and they tell us that px minus 3, the whole thing q, will actually be equal to 512 x9 minus r x8 plus blah blah blah. So there's 3 unknowns, p, q, r, and we need to find them all. So this one is a lot more exciting, right? What we will do is we are going to start with the person on the left. P, oh man, why are you like so ugly? Right, px minus 3 q. We're going to start with this guy, and we're going to use binomial theorem. It's going to give us the first object like this, the second object. I don't know if you heard the hiccup. That was me hiccuping. Don't be alarmed. And the second object will be like this. There are more objects, but we don't actually need to care about the rest, because on the right hand side we only have two different objects. So this guy over here, right, we will simplify him into p to the power of q, x to the power of q, plus, well, sorry, not plus, minus actually, minus 3q p to the power of q minus 1, x to the power of q minus 1, plus blah blah blah. So from here, we will combine these two, and we will say that pq xq minus 3q p to the power of q minus 1, x to the power of q minus 1 is identical to the first two objects that they have given us. Like this. From here, this becomes a polynomials question, right? All we need to do is to compare things side by side. The very first and probably easiest comparison is to take a look at the x on the first object. From here, it is very, very clear that we have q equals to 9. And because q is equal to 9, I can also go on to say that this guy here and that guy here are the same. And so p to the power of q, which is 9, will be equal to 512. But 512 here is equal to 2 to the power of 9. And as we learned in the previous video, this will just allow us to compare the bases. P equal to 2. So now that we have found P and Q, then the last thing we need to do is to find R. And if we do a direct comparison, we will see that R over here, right, is in between the minus and the x to the power of 8. Of course, Q is equal to 9, so Q minus 1 is 8. So the in-between object will actually be, oh, made a mistake. So the in-between object will actually be this guy. And therefore, we will conclude that R is equal to 3qpq minus 1. In other words, 3 times 9 times 2 to the power of 8. And this will give us 6912. And therefore we are done. P equal to 2, Q equal to 9, R equal to 6912. The end. Alright? So in this case, it's not so bad. The unknowns are inside the binomial expansion. If the unknowns were on the power of the binomial expansion, then that will be a lot more scary. So the next problem, problem 6, is a mix of general, well, maybe not general term, but just a mix of polynomials in general, as well as some trinomial questions. So looking at 6a, they want us to find the coefficient of x to the power of 3 inside x squared minus x minus 2 multiplied by x plus 1 cubed. So before we begin, let us play cheat by flipping the order, because when you have 1 in front, you can use the easier simplified binomial theorem formula. Of course, by Pascal's triangle, I will just have 1, 3, 3, 1, like so. And from here, you can ask yourself, how do I get x cubed? So the first method is like this. The second method is like that. And the last method is like this. So we will deliberately pick and choose these particular multiplications. So we will have 3x cubed. Let's see, minus x times 3x squared. Oh, minus 3x cubed. And then afterwards, minus 2x cubed. In other words, minus 2x cubed. Implying, of course, that the coefficient will be equal to 2, and we are done. So the first problem is kind of a warm-up, nothing much to say. The second problem we have over here tells us, okay, can we find the x squared term inside this trinomial? So now we have a different situation. We have 2 plus 3x. Wow, can this thing cooperate? Plus 3x, thank you, minus 2x squared. And then the entire thing is raised to the power 4. So obviously this is a trinomial over here. You do not want to do this raw. It would be a lot more digestible if you could change it into a binomial by using substitution. Right? So the strategy will be, fortunately, the same as always actually. We will take the second and the third object, right? In other words, we'll take these guys and we will do substitution. Like this. Right, so in doing this substitution, it will naturally create for us a binomial, and from there we can go on to our tried and tested methods of working things out. So in this case, what we expect to see is we will have, give me a moment, we will have the following: 2 plus u to the power 4, and from here we will use our binomial theorem formula. Actually, now I'm just going to use Pascal's triangle for the coefficients. 1, 4, 6, and then we will ignore the rest. Why do we ignore the rest? Because the problem said until, or rather the problem said to find x squared. So anything more than power 2 becomes irrelevant. So from here we will have 16 plus 32 u plus 24 u squared plus dot dot dot. Now over here, if you are focusing only on the objects that give you x squared and nothing else, then we can clearly tell that you are only interested in this part, and you are interested in this part square attacking that guy. That's the only thing we want. So let us do that. 32 negative 3x squared plus 24 3x entire thing squared. And everything else is irrelevant. The constant is irrelevant, the x power 1 is irrelevant, the x power 3 and onwards is all irrelevant. So we get to cancel a lot of nice stuff. Once you are here, then we can go on to simply combine everything together, right? So in this case, the coefficients will clearly give you, let's see, negative, wait a minute, I just realized that this thing is not 3, it's going to be a 2. So help me adjust that, like so. Right? So we're going to have negative, let's see, 64 x squared plus, and over here we'll have 24 times 3 squared, in other words 24 times 9, which will be 216 x squared plus blah blah blah. Now obviously this implies that the coefficient will be equal to negative 64 plus 216, which will be 152. And then we are done. Right? The last problem is another interesting one. We have a quadratic multiplied by a trinomial. One thing I do have to say, however, before we begin, is that there's a major typo over here. The question does not want you to find x. The question wants you to find x squared. So please help me change that for those of you who are in my class and have the worksheet with you. This also means that the answer sheet answer will be BS from here on forth. So I'm afraid you're going to have to actually look at my working for this part. Right, so 6c tells us to work with 7 plus 6x plus 5x squared multiplied by 1 minus x plus x squared to the power of 5. Just like the previous problems, we will use substitution to change the trinomial. In this case, looking at the last two objects, I can let u equal to x squared minus x. And this gives us 1 plus u power 5. From here, it will be simple enough to open everything up. I will use Pascal's triangle. We will have 1, 5, 10, and then the rest are irrelevant because the question only cares about x squared. Once we have this, we can go on to replace the u, right, with the actual object. And once again, we need to be aware of what is relevant over here. In this case, if you look at this guy, you will notice that he actually turns into x4 minus 2x3 plus x squared. And only this guy over here will be, and only these two guys over here will be relevant. Right? The x power 4 is completely unnecessary. We're only interested in this guy. Sorry, this is my bad. Because x power 3 is also overshot. The question only wants x squared. Right? So from here, we can actually just streamline the process and focus only on the x squared that will come out of that internal binomial. And therefore, it will give us an x squared here. Like this. From here, we will tidy up our work. And once you are here, then we can ask ourselves, how do we get x squared? I think this one is quite simple. You can go this way, or you can go that way, or you can go this way. A nice little rainbow expansion. So the coefficient will be 7 times 15, let's see, plus 6 times negative 5, plus 5 times 1. And this implies that the coefficient will be equal to, and then from here you can just feed it into your calculator. You should get a total of 80. Right? Pretty straightforward, all things considered. So we are left with two more problems. Now these are the bad boys of today's lesson. Both of them involve finding the value of an unknown power. So let's take a look at question 9. 9 tells us when x squared minus 2 over x to the power of n is expanded in descending powers. So you start from the biggest power. The third term has a coefficient of 112. So let's just do this immediately. The first object will be like this. The second object will be like that. The third object will be like this. Right? So from here, they say that the third object, the third term, has a coefficient of 112, which means that, therefore, the third object, n choose 2, x squared, n minus 2, negative 2 over x squared, has a coefficient of 112. Now what does this mean? It means that if I could just separate all the numbers, all the coefficients from the x, then whoever is on the left hand side, whoever is the coefficient, must be 112. So let us do the separation straight away. Over here, we will use our laws of indices to get this result. like so. And this implies that for n choose 2, which is the coefficient, will be equal to 112. This further can be simplified to give us n choose 2 equals to 28. So far so good. So once I have n choose 2 equals to 28, we can go on to find the value of n. So n choose 2 will give us n minus 1 over 2. This is from the formula sheet, right? Equals to 28. Why is it n minus 1 over 2? It is because of this particular formula all the way at the very beginning. Specifically this one. Right? So you can just imagine r is equal to 2. So n minus 1 over 2 equals to 28. Obviously this means n squared minus n equals to 56, implying n squared minus n minus 56 equal to 0. Once you are here, then we will therefore have n minus 8, n plus 7 equal to 0, implying n equals to 8 or negative 7. Right? Now, we will obviously reject the negative one. So now we have n equals to 8. From here, the n equals to 8, we can then go on to ask ourselves, how do we find x power 7? So now that n is equal to 8, we can move on to the next part of the problem, which is to find the coefficient of x to the power of 7. So I will simply say that inside x squared minus 2 over x to the power of n, which we now know is 8, the general term tr plus 1 will be n choose r, a to the power of n minus r, b to the power of r. We can go on to simplify this result. Right, so we can actually go on to perform this simplification. Quite straightforward. Nothing I don't expect you to be, just having any issues with. One other thing I do need to take note of, however, is you notice I tend to have this habit of putting all the numbers like this and all the algebra on this other side. Right? Of course, this is just by using laws of indices, so it will be helpful for you to cultivate this habit. Again, it's laws of indices, so I don't expect you to have any issues. Same for all the arrangement just now. I don't expect you to have any issues with this part. From here, we will say that so the power 16 minus 3r will be equal to 7 for the x power 7 term. Right? So in this case, it is clear that r equals to 3 in order to get power equal to 7. And if r equals to 3, then we can say that the x7 term will be t3 plus 1, which will be negative 2 to the power of 3, 8 to the power of 3, 8 choose 3, x 16 minus 3 times 3. And this will give us negative 448 x to the power of 7, which implies that the coefficient is indeed negative 448, which is what we wanted to show in the first place, QED. And we are done. Right? So nothing exceptional here, honestly. The last problem of the day is question 10. Question 10 tells us, okay, we want to find the value of n and the value of a. And they have given us some very incomplete information. So let's have a look. We have 1 minus x over 2 to the power of n equals to 1 plus ax plus 7x squared plus blah blah blah. Right? So let's ignore what they've given us for now. Let's try and open this thing up by ourselves. The good news is the first object is 1. So you can actually imagine this as this situation. And then afterwards, just use the easier binomial theorem formula. So I'll have 1 minus n over 2 x plus n choose 2 x squared over 4. Okay, for consistency's sake, let me write that as 1 over 4 n choose 2 x squared. And then this thing will be plus dot dot dot. So from here, this will be a polynomial identity with 1 plus ax plus 7x squared plus dot dot dot. So once we are at this stage, it is easy for us to compare the coefficient of x squared and say that 1 over 4 n choose 2 equals to 7. This implies n choose 2 equals to 28. And just like the previous problems, we will be able to change the combinatoric into this result. This will then give us n squared minus n equals to 56. In other words, n squared minus n minus 56 equal to 0. In other words, n minus 8, n plus 7 equals to 0. Right? And therefore, we will say that n is equal to 8 or negative 7. We will obviously reject the negative one. And so, from here, we will do a second round of comparison. This time round, we will compare plus a with minus n over 2. Make sure to compare with the minus, alright? So from here, we will have a equals to negative n over 2. And n, we have already found is 8. So this will just give us negative 4. And therefore, you notice we have gotten n equals to 8 and a equals to negative 4, which is what we wanted to show, QED. And we are done. Right, so up to this point, that will be all the content, all the practice exercises we have for today. So if you have nothing else for me, I have nothing else for you. You are dismissed. Alright, so congratulations on making it this far. We have covered so much stuff that Christmas has already flown by, right? If you look at the bottom right, the time now is almost 1 AM. So yeah, this was my Christmas. Feels bad, but it's alright. So up to this point, we are already done with the algebra section, right? If you remember the very first video, we have the Sec 3 and the Sec 4 stuff. Sec 4 is basically calculus, which will be differentiation, integration, and some kinematics. We will also learn some geometry, feels bad. As for Sec 3, we have quite a lot of different things. We have algebra and powers. We have graphs and coordinate geometry, right? I cannot write. And we have some advanced trigonometrical identities and proofs. So we are officially done with this guy, the algebra. Now the graphs and the coordinate geometry will not be so bad. I expect to be done within 2 to 3 videos. And then trigonometry I expect to be done within 2 videos. So congratulations, we actually only have like what? 4 to 5 videos left, right? 4 to 5 videos. And we will be done with the entirety of the first year of additional math. So congratulations. From there on, I will decide whether to move on to the calculus videos. It will not be a priority, of course, since those of you who are watching these videos are all Sec 3 students right now. So we will see how it goes from there. Alright, so if nothing else, let us call it a day over here. As usual, thank you to those of you who are watching live. For some reason, I have a lot of playbacks today. I think for this particular video, it's because of the late timing, right? At this time zone, we will just, see a lot more of overseas viewers coming in. So maybe that's why. It makes sense because if I were a Singaporean, I would not willingly watch this kind of video, right? Because we already see too much of this in school. Unless I'm like studying myself, in which case it makes sense. Let's see, question in the chat. Coordinate geometry is going to be vectors. Actually, no, the vectors is going to be in the elementary mathematics. For additional mathematics, what we will do is we will learn about parallel and perpendicular lines. We will learn how to find the area of a polygon when the polygon is drawn as a graph on the x and y axis. We will learn about linearization of difficult functions such as logarithms. And we will also learn about the graphs with a y-squared term inside them. The main example will be the graphs of circles, right? So we will be doing that as well. And then we will combine it with some earlier concepts such as the discriminant. So the coordinate geometry section isn't very long. Trigonometry will be more interesting. We will talk about the 4 quadrants. We will talk about special angles and the graphs of trigo functions. We will talk about how to solve algebra problems in trigo. And then we will learn how to do trigonometry proofs, which will be a very serious topic. Okay, so once again, thanks to all my live viewers for watching. Next time I will move on to our next segment, the graphing and the coordinate geometry. So I hope that will be a fresh, a breath of fresh air, a nice little change of pace for all of us here, right? So one last time, thank you all for watching and for belatedly paying me company in this extremely mediocre Christmas evening, right? So see you guys next time.